Okay, let us see another example on buoyancy and stability of floating bodies with some metacentric height design. So the design of floating bodies often requires the use of lightweight materials that offer a high degree of buoyancy. So with low specific weight and density, and the material should have little or no tendency to absorb the material or just the fluid, and also compatibility with the fluid in which it will operate, and also it should have just an ability to be formed to appropriate shapes, and also ability to withstand fluid pressure to which it will be subjected, and also abrasion resistance, and also damage tolerance. So the floating material or object should just fulfill such criteria for any purpose. It could be boats or ships, etc. So let us see a block with dimension this one 6, 2.5 and 1.5 meter floats horizontally in water. So it floats horizontally. Find the volume of water displaced and the position of the center of buoyancy. So we are going to calculate the center of buoyancy and what is the buoyant force and what fraction of the block is above water surface. If the block is immersed with 0.65 meter, and what is the metacentric height? So take density of the block, you have density of the block is 650 kilogram per meter cube, and density of water is this one. So accordingly, you can check now. So I think in the previous buoyancy and the principle of flotation, so the magnitude of the buoyant force is equal to the weight of the displaced fluid. So I think with that concept, let us start now. Let us start. So we will have some metacentric position. So if the meta m, if m is greater than g, stable equilibrium, which is positive, and if m is less than g, which is the center of gravity of the object, unstable equilibrium, and if m is equal to g, neutral equilibrium, which is 0. So metacentric height we will calculate now. Gm is equal to bm minus bg. Let me show you some illustrative sketch on metacentric position and also writing moment, etc. Let us see. So this is if m is above g, if this is the object which is floating, which is a stable equilibrium. So if m is greater than g, then you have something, this is moment, so we will calculate gm. So it is just a stable equilibrium. If m is below g, so if m is below g, which is just center of buoyancy at this point, and g is at this point, and m is here. So if m is below, so we will calculate negative calculation, just unstable equilibrium. Otherwise, if g and m coincides, then neutral equilibrium. So just it will be collinear, then we will have no further displacement will occur. So I think let us solve this example in detail. So first you have to compute the volume of the block according to the dimension. So with a given dimension, you can find 6 multiplied by 2.5 times 1.5, then it will be 22.5 meter cubes. This is the volume of the block. So weight of the block can be computed now. Weight of the block, density of the block times G, which is unit weight of the material, times volume of the block. So this is the weight of the block, which is 3471 Newton, or 143.471 kilonewton. So according to the previous principle, a body floats if the density of the object is less than the density of the liquid. So for equilibrium, we have weight of the block is equal to weight of water displaced. So according to this principle, we can find the weight of the block is this one. So what is the volume of water displaced? So we can find volume of water displaced will be weight of water displaced over weight density of water. So I think this is nothing, just gamma times V or unit weight times V. So you divide weight of water displaced divided by rho G. So you can find this is the volume of water displaced by the liquid. So this is the volume of water displaced. So the volume of wooden block in water is equal to the volume of water displaced. So you can just cancel G, then you can find volume of wooden block in water is equal to volume of water displaced. So 6 times 2.5 times height of immersed is equal to the volume of water displaced. So to find what height is submerged in water. So the height of water will be computed. This is 0.975 meter. So this is height of immersed. So if we find this is the height of water immersed by the block. So center of buoyancy will be P over 2. You simply divide the height of submergence by 2. So you get this result from the base. From the base, we find. So center of gravity, again, 1.5 divided by 2, 0.75 from the base. So compare B and G. So center of buoyancy, which is midpoint of the total B, which is total height of water, which is submerged, half of that, we calculate 0.48. Then, since G is greater than B, from this B is less than, or G is greater than B, clear? G is greater than B, center of gravity. So it is unstable. So we will have some metacentric height. So the buoyant force, which is equal to the weight of the block, which is equal to the weight of the displaced fluid, which is 143,471. So 143.471 kilometer. Okay. So once we find the buoyant force, then we can go to when the block is immersed with 0.65 fraction can be computed. So weight of the displaced fluid is equal to the weight of the block. So rho G V of immersed water is equal to rho B, which is density of the block, G times V. So cancel G both sides, so you get this equation. So this is the general equation for any flotation. So volume of water, which is displaced or immersed, divided by the volume of the block, total volume, is equal to density of the block divided by density of water. So fraction above water surface can be computed now. So percentage fraction above water surface will be from the total 1 minus this volume of immersion divided by volume of block. This is percentage fraction underwater. So you just from 100 you can subtract. So you get this one. Fraction percentage of fraction above water will be 56.67, and percentage of fraction below water level, below water surface can be computed. So total, which is 0.65 divided by 1.5, which is 43.33. So this is important. So when the object is immersed with this dimension, you can find percentage of fraction below and above water. So from A, above, the actual depth of immersion of the block is this one, actual, from calculation. From calculation, due to the object density and weight, and also due to the above calculation, you have height 0.95 meter. Then center of gravity or D, we have 0.75, which is A to G. A to G from base. This is the base. From this base, up to this point, you have AG 0.75, half of 1.5. And you have center of buoyancy 0.487, which is AB, from A to B. So metacentric height can be computed now. Since it is unstable, the result should be negative, clear? So BM plus or minus BG. So this is GM is metacentric height, so BM minus BG. Since G is above, B takes the negative, so plus or minus will be just under consideration. So take negative, then result will be calculated. So BM will be GM can be computed. So first you have to find BM. BM is moment of inertia divided by volume of the displaced fluid. So Moment of inertia about y direction, which is this direction. Just this is the base of the block. So just water is going through this. So it will just going like this. It will go like this. Clear? So the base. So we will have moment of inertia about y direction, which is just b h cube over 12, which is 45. Then you can find bg, ag minus ab. You have this result, which is from the above 0.263. Then gm equal to moment of inertia over volume of the displaced liquid, which is just in the column, minus bg. So you get this result. So once you compute gm, this is the metacentric height. Then since bg is less than gm, bg is less than gm, bg is this one, then m lies below g and b. This shows an overturning moment which is unstable. Overturning moment is produced, hence it is unstable. So you can see these sketches. So if the weight and the reaction force is going through the center of the object or center of gravity, then it will be equilibrium. Otherwise, if it is not in the same direction, if this is going through this direction, but this is through this direction, then there is unstable or overturning couple. So you have this sketch. So you have this is stable R and W going through the same line, G, B, the same point, collinear, but here different points. So you have overturning moment with this X. Then we find this equation. So you have GM, metacentric height. Then PM is already completed. Then from moment, then finally we found this result. So this is sketch for metacentric heights. So I think metacenter, just as a conclusion, metacenter represents the point where the vertical line through the center of buoyancy intersects the line of action of the buoyant force. The force when the floating body is slightly tilted, like ships or boats. Sometimes they just make tilt. So it acts as a pivot point, about which the body rotates when disturbed from its equilibrium position. So this is from the previous I have shown you. So if you have something big, please just comment on this, then we will discuss. So this is a board, just a sample sketch for a board. So you have here just axis input, then we can just design just boats. Actually, boats and ships made of different just wood materials and also aluminum and etc. is different. So average density of this boat just it should float with respect to the sea water. So I think in design of boats and ships, we are using the principle of flotation, which is buoyancy and flotation. So with respect to the weight or the load inside the boat or shore ships, just we will compute different aspects, how it is floating and how it is going. So it is more detailed in the next or in the next topic or sessions. Thank you. Okay, so this is all about today's tutorial. Hopefully you liked the video. If you have any comment or doubt regarding this topic, please let me know and write down in the comment section below. I will definitely reply on it. So please like, share this video with your friends and subscribe to my channel to get more videos on similar examples. Thank you very much for your attending.